You're listening to the Common Descent Podcast. Hello, Will.
Hello, David.
Hello, listeners, and welcome to the Common Descent Podcast. This is episode 137. This episode's topic is fossilization.
It's about time we mentioned that.
Yeah, if you're just joining us, the Common Descent Podcast is a podcast about paleontology, evolution, and the fascinating diversity of life, past and present. And as of the beginning of 2022, we've been doing this podcast for 5 years, so we figured now's as good a time as any to talk about what a fossil is.
Yeah, you know what? We've kept you eagerly waiting.
It's what the people want. This episode, we are going to go in-depth into fossils, the fossilization process, how fossils are formed, how the formation of fossils, how that process influences what we end up getting at the end of the process, and the many ways why it is invaluable for paleontologists to understand the process that the fossils have gone through before we get the chance to study them.
Yeah, we don't just learn about fossils by what it is, an arm, a leg, a shell, a leaf, but also by how it got here. How it became a fossil tells us a bunch, which is, I love it. It's one of my favorite little aspects of paleontology.
Yeah, this is going to be a fun episode. We're discussing this episode because it is a very important topic to talk about, but also because it was requested by a bunch of our listeners. This topic was requested by Jonathan, Corbin, Dr. J, Thomas, Lewis, Morg, and Mark and Colleen.
Wow, good suggestion, everybody.
Yeah, people want to hear about this.
Please explain what you're talking about.
All that discussion will happen in the main portion of the episode, but before that, we're going to do a bunch of news, and before that, we're going to do just a couple of announcements.
Okay.
This episode, like all episodes, is brought to you in large part by the support we get on Patreon. Subscribers to our Patreon get all sorts of goodies. They get director's notes, they get Patreon live streams that they can join with us, they get bonus content. In fact, we just recently released bonus news and after chat for the month of March. It is a meaty after chat. We had a lot of fun.
We had stuff to say.
We had a lot of opinions to express. So if you are a patron and you're not listening to those, check them out. And if you are not a patron, maybe consider patroning for us.
If you're not a patron, you'd like to listen to those.
Right. Another one of the rewards that patrons can get is at a certain level, we will shout their name out here on the podcast when they join. So this episode, we would like to shout out our new patrons, Keegan, Jackson, and Coulter.
Welcome. Thank you so much for your support.
Thank you very much. Hey, speaking of ways that you can interact with us and support the podcast, we are on all of the social medias, of course. We recently, at the beginning of this year, launched a Discord server.
Yep.
And we are currently in the process of planning more events and special occasions to do on Discord. So if you're on the Discord server, stay tuned. We're going to be doing some more Q&A type stuff, things like that. Another thing we launched at the beginning of this year as part of our 5-year anniversary celebration is a bunch of new art on our Zazzle store.
Mm-hmm.
Cool shirts and other merch depicting fun cartoony things and fun paleo-arty things that we think you'd all very much enjoy. If you haven't already, check our Zazzle store and see if there's any merch you want. You can find a link to that and the Discord server and all of our social medias in the episode description. Oh, hey, one other thing we're doing as part of our 5-year anniversary celebration is in June and July this year, we will be celebrating official, for the podcast, Croc and Snake Month.
Woo!
We are also currently in the process of making the final plans for what those are going to look like, so stay tuned.
It's going to be fun. It's going to be a lot of fun.
As promised, now that we are done with announcements, it is time to move on to the news. Every episode, we gather up some news from the world of paleontology, evolution, and the fascinating diversity of life past and present, and we deliver it to you so that we stay up to date and you all stay up to date and we all know what's going on out there on the leading edge of science. Will, I thought you could start today.
Oh, thank you.
Yeah, go ahead.
I appreciate that.
My gift to you.
I have some news about giant croc trace fossils from Canada.
Okay. I like trace fossils. I
Yeah?
like Canada.
Yeah?
Crocs are okay.
This is research by Guy Plint, Charles Helm, and Martin Lockley in Historical Biology, and the article is by Guy Plint and Charles Helm in The Conversation. This research is on some new, or at least recently described, trace fossils from the Cenomanian-Dunvegan Formation in northeast British Columbia. This is a delta plane strata, so the rock's preserving a delta plane that was about 95 to 97 million years old, so Cretaceous, which is already a formation well known for dinosaur trackways.
Okay.
So footprints and movement traces in the mud.
Right. For more information on footprints and other trace fossils, check out episode 118, which was all about trace fossils.
Yeah. This environment would have been a low-lying delta plain, so shallow lakes, river channels with vegetated wetlands around those bodies of water.
Good place for leaving footprints.
Absolutely. Lots of silty mud. As I already said, well known for dinosaur footprints. The area that they were describing and the traces that they were describing included a lot of ankylosaur footprints.
The armored dinosaurs from episode 69.
And other ornithopod dinosaur.
Sure, we haven't done an episode about that yet.
So, yeah, whatever. Walking traces have been, and wading, from them moving in the water and their feet hitting the ground as they're moving through the water, have been preserved from both of those groups. The big deal thing that a lot of the news articles are focusing on in this research is that there are crocodilian swimming traces and tracks preserved as well that seem to indicate very large crocodilians.
Oh, crocodilians, episode 2.
So, many of these traces are actually from them swimming, their feet hitting the ground.
Right, not a full footprint like we normally think of it, but kind of a scrape mark as they gently touch off the ground.
Which was something that I didn't even really knew that we had swim traces.
Yeah.
Which is very cool. I just hadn't ever thought about it. This is not the only fossil site with these kinds of traces. They are found elsewhere. But some of these are extremely well preserved. They said some of the feet, the portions of feet at least, preserve the scale pattern.
Wow.
So really nice trace of these swimming patterns. They were able to note a number of interesting things about the traces they were finding. One being that the analysis of the deposition of the strata, so when sediment's being laid down, shows alternating phases of flooding and land being exposed. So water coming in and water leaving land exposed.
Gotcha. So kind of like a tidal area, but in this case, a river occasionally overflowing.
Exactly. And that this would have an effect on two major things. One, the consistency of the mud, firm versus soupy mud. So that leaves different kind of trace fossils when a foot goes into very soft or very hard mud. But also whether the animals and where the animals were walking or swimming.
Oh, yeah.
One area might be walked through during one time and then swam through another time.
Yeah.
When it's flooded. So they found alternating, you'd have swimming traces next to walking traces because of in the same area because of when it was flooded and when it wasn't.
That's very cool.
This does, though, have an effect on the accuracy of being able to determine some foot traces, because on soupy mud, it might not be as good or clear whose foot we're seeing.
Mm-hmm.
And there are some traces that look very similar to both croc and ankylosaur because the features aren't clear enough. So they said that typically the way they determined it, and I thought this was just fun, is that if there was no tail drag mark, probably ankylosaur, because they tend to hold their tails up.
Right.
And if there were prominent claws, probably crocodilian.
Because they have prominent claws. So they had ways of determining who was who when the feet were muddy. And they were able to determine who was hanging out where more often, with ankylosaur traces being much better preserved in lake and channel margin deposits. So along the edge of the waterway.
While the crocodilians were more commonly preserved in the more muddy lake sediments.
Right.
So
the deeper water.
Where they're swimming.
Makes total sense.
But the really big news that all the news articles are focusing on is that the traces of these crocs indicate large crocs.
Ooh.
Now, when I say large crocs, I don't mean as big as ours today. They estimate, based off of this, that these crocs would have been somewhere around 9, maybe up to 12 meters long.
Oh.
So these are pushing 30 and more feet, which is big.
Which is 50% more, at least, than our modern largest crocs.
These would have been weighing around like 5 tons if they were crocs at this size.
That is an elephant croc.
And they estimated this by the distance across the foot from claw to claw.
Wow.
And scaling up what we would expect. This was corroborated by the identification of other partial tracks that measured 75 centimeters long.
2.5 feet.
So a very big foot, which also estimates out to about a 9-meter croc. This is notable for a couple reasons. First, the trackway evidence of large crocs like this from Canada. So, cool.
Yeah, not a place we associate with crocs today.
But also, the age of the tracks is important. Before this, the earliest evidence of giant crocodilians in North America was Deinosuchus.
Okay.
Which is about 82 million years old.
Oh.
A bit younger than this fossil site. Now, they're also estimated to be on that upper 12 meter. These are one of the biggest crocs that ever lived. And they're recorded from the United States and Mexico. They have not been found in Canada before. So this is the first evidence of large crocs in Canada, but also earlier than Deinosuchus.
Yeah.
Which could mean that this more northern giant croc could be a precursor, either some relation or just an earlier giant croc before Deinosuchus became prominent in North America.
Yeah, that this could be part of the same lineage of giant crocs as Deinosuchus, or this could be a separate evolution of giant size in crocs.
Which is something we see throughout crocodilians, that, as they said, giantism has evolved multiple times in this group.
Right.
To this size range very regularly. So we have earlier evidence of a similarly sized giant croc in North America before we have fossils of Deinosuchus.
Yeah, this is a cool feature of the trace fossil record. Because as we've discussed previously in other news and in episode 118 about trace fossils, we don't tend to name species off of footprints.
Because we don't know what that species foot actually looked like.
Right. It's very hard to link a footprint to a skeleton, and skeletons are what we use to identify species. So the authors aren't identifying a new species of ancient croc, but now we have evidence of the existence of a giant croc to look for.
Yes.
In nearby and similar age sediments, which is a very cool kind of evidence to have.
We also now know that North America was sporting crocs of this size 13 million years earlier than we thought.
Yeah. Now, Deinosuchus is part of the alligator lineage.
Yes.
And Purosaurus from South America in, I think, the Miocene is a caiman.
Mm-hmm.
And Sarcosuchus, which is also Cretaceous, if I remember right, is sort of outside all of the modern groups, isn't it?
Yeah, they are not actually Crocodilus.
So, what group do we hope this giant... Do we hope this was a giant gavial?
That would be awesome. There is gharial-shaped giant croc.
Okay.
I don't know where they fall out. And I bet due to the slender snout, a lot of people are asking that question.
Yeah, probably.
But a true croc, a crocodilus.
A crocodile.
Yeah, a crocodile would be cool.
Yeah, that'd be pretty cool.
There are 2 other fun notes. One, the fact that there are coexisting tracks of swimming crocs and walking ankylosaurs in the same spot makes this a very unique fossil trackway.
Oh, yeah.
Like, that's not something we really see very often in other trackways, so that just makes this kind of an oddball standout. And one of the tracks from one of the ankylosaurs, one of the ankylosaur trackways represented, is the smallest thus far described.
Oh.
Just 10 centimeters wide.
A little baby ankylosaur foot.
Yeah, so there's interesting things other than the crocs. But mostly the crocs.
But that's why we're talking about it. Well, since you started off your news with a trace fossil example, I also have trace fossil news.
Oh.
Also Cretaceous-aged footprints.
How big is your croc?
There is no croc.
Oh.
This is a dinosaur whose footprints show evidence of an injury to the foot. Yeah, this is awesome. This is research by Carlos Herrera Castillo et al. In the journal PLOS ONE, and we will link to an article in the blog post. Every episode has a blog post corresponding with it on our blog. Links in the description. We will link to these news articles. This one is in Science by Rodrigo Perez Ortega. The trackways in this study are left in limestone in a fossil locality in Spain known as the Las Hoyas locality. This is early Cretaceous, so 129 to 127 million years old or thereabouts. So still Cretaceous, but significantly earlier than those croc tracks. This trackway consists of 6 footprints, 3 left feet, 3 right feet.
Cool.
Left in shallow water, so this was another sort of wading dinosaur across a shallow water area, walking through a microbial mat. That's what the footprints are left in.
Cool.
Is this sort of muddy microbial sediment.
It's get between your toes.
And you were talking about swimming traces. I think we've mentioned this before. This trackway is left in a deposit that also shows a lot of fish swimming traces.
Nice.
So you can get these little swoopy marks that are left by fish tails as they gently touch down on the sediment as they swim by. So this dinosaur walked through an area where a bunch of fish were swimming around in this shallow ocean water.
Anytime we get a trace fossil preserved, there's always a little part of me that's like, man, how did that not get messed up?
Mm-hmm.
But something as subtle and delicate as fish swimming traces?
Yeah.
Wow.
Boy, fossil record's pretty cool. We should do a whole episode about that.
Ooh.
The dinosaur tracks in question, like I said, there are 3 right prints and 3 left prints. The right tracks are tridactyl, meaning they have 3 toes.
Cool.
Like we see in theropod dinosaurs very commonly, like your T-Rexes and etc. They're each about 44 centimeters long, so about 18 inches long. The left tracks are slightly shorter and deformed.
Mm.
In this study, the researchers analyzed the shape and structure of all the different prints, compare it with other dinosaur tracks, and here's what they found. First, they were able to determine based on the size and shape and relation to each other in space of the tracks, that even though the right and left are slightly different shapes, they do appear to have belonged to one animal. They show a straight, consistent path, that this was an animal walking in a straight line, left, right, and a consistent gait. Like the feet are all in line. That doesn't show any evidence of a limp or anything, which we have found, apparently, in some other fossil trackways.
Awesome.
They're able to estimate that the dinosaur that left it probably had a hip height of about 2 meters, so 6 feet tall, and was probably 6 to 7 meters long. So in the 20-25 foot range, so a good-sized theropod.
Yeah, I wouldn't want to be in front of it.
And it was walking about 4 kilometers per hour or 2.5 miles per hour. So you could outrun it.
Yeah.
But, of course, the really interesting thing, and the thing that sets it apart, the left foot, what's wrong with it is that instead of 3 toes, the footprints show a nice outer toe, a nice middle toe, but the inner toe only is leaving short, irregularly shaped impressions.
Oh.
Likely because the toe was broken or missing. And indeed, some of the tracks lead the authors to suspect the toe might have been backwards. That it was crooked or curved incorrectly because it was either broken or deformed.
Yeah.
And this was left in the footprints. It left wrong footprints. Now, I mentioned earlier that they didn't notice a limp, like it was walking consistently, but they did notice some unusual features of the way it was walking. Compared to other dinosaur trackways that we know, this dinosaur had an unusually wide stride. Its feet were wider apart as it was walking than we normally expect from dinosaurs like this, and in conjunction with that, the steps were a little shorter.
Gotcha. So walking like a cowboy.
Yes.
With your legs apart.
Yeah, it was adjusting, it was widening its stance, probably in response to having an injured foot. And they described that certain ways that the sediment is deformed around the right track, the good foot, indicates that it was putting more weight on the right foot. So it wasn't limping, but it was walking more slowly and more carefully because one of its feet was missing a toe.
Interesting. That's really fascinating because that's something that we see in people who get injured today, and they adjust the way, even if you do it subconsciously, you adjust the way you're carrying your body to try to nurse whatever injured section you now have. to be able to tell that from footprints.
How cool.
Oh.
There are also some interesting comparisons with other theropods. First, birds. Apparently, according to the paper, we see similar things in modern birds sometimes. Particularly in domestic birds, we'll see what are called crooked toes or curled toes, which can happen due to genetic abnormalities or dietary issues or other problems. And they also point out in the paper that it is not uncommon for us to find theropod dinosaur skeletons with injuries to the innermost toe. The same toe that is deformed or missing or broken here. So it sounds like this toe was just apparently particularly prone to having things go wrong with it, which means that there could have been quite a number of dinosaurs over the millennia walking like this one with just a broken toe they had to deal with.
Yeah. I wonder what they were doing to injure that inner toe.
Yeah. I don't know if it's just that it's smaller or more delicate or what, if it's a feature of the toe.
Yeah, is it that toe is distinct somehow that makes it prone to injury?
Right. Because otherwise, if it was just an environmental thing, you'd expect it to be the outer toe.
Yeah.
The one that you stub on stuff while you're walking around.
Well, and that was the first two thoughts that came to me behaviorally, is that if there's something about their stride that puts that toe in danger, if you walk with your feet splayed a particular way, it's going to change which toes you're more likely to hit things with when you walk around at night.
Yeah.
So, like, maybe there's something about the way they walk. Or the other idea that came in is if they're using that toe, like, if they kick at each other when they are fighting or something, if that's the toe they're aiming at. Because if you break that toe, it's the inner toe and it's fine, but I still want to kick you. But I don't want to kick you with one of my good toes.
It also makes me think of the rhino from the Gray Fossil Site that had broken inner toes that was possibly, based on comparisons to similar injuries in modern rhinos, incurred during getting up close and personal with another rhino.
Yes.
Either in fighting or mating.
Yep, that would make a ton of sense if this was bad dance partners stepping on your little pinky toe.
You've got 1.5 right feet. And then one last little note that I think is a wonderful parallel with the news that you just discussed. These trackways are the first record of a large theropod in this ecosystem.
Cool.
This fossil locality does not have any skeletal remains of a theropod this big. So also, this broken-footed dinosaur is something we haven't seen in this location before. So just a whole bunch of cool info bundled up in some tracks.
Fantastic. Well, my next news is not about trace fossils.
No.
And in fact, it's not even about fossils.
Oh, that's the theme of the episode, though.
It is, I know. I'm straying, but it's real neat.
All right.
This is about studying evolution in cities.
Okay.
And
not a lot of fossils in cities.
Not a lot of fossils in cities. I assume the city millions of years from now will be looked at much like a tropical rainforest. And that things are recycled and cleaned up too quickly.
Right.
But this is about evolution, studying evolution of life in cities, but particularly this is a review on how to do it most accurately.
Okay.
This is research by Sarah Diamond and Ryan Martin in Annual Review of Ecology, Evolution, and Systematics. And the article is by Eric Bender and Knowable Magazine in Inverse. So urban evolution is what this is talking about. The genetic changes we see in wildlife among city environments.
Right. City animals, I often think of the insects and the birds and the rodents that make their homes among the city.
But this also includes all the plants that grow up between the sidewalk.
Oh, yeah.
Any microbes that we find in the water or bodies of water among the city. So anything, sometimes it's animals that have moved in like rats, but also it's just the things that we've built around and now they're still just living there, but there's a city around them now. How does living in a city affect these different categories of life? This is not new research. I mean, it's as new as cities are, but this is not new field of study. So this isn't something that they're like, hey, we should look into this. There's been tons of studies and there's tons of examples of evolution we've witnessed or think we are witnessing in different groups of life that is almost surely directly because of the city ecosystem we've created around them or created for them to live in. By far the most famous of these is the English peppered moth,
Mm-hmm.
which were typically white, and then the Industrial Revolution came around, and now the white lichen-covered trees they hit on became sooty, and so the rare black or dark-colored peppered moth became the more successful and the more common, and then when the pollution was controlled, it went back when the soot was no longer a problem. That is a direct evidence of natural selection being driven and adjusted by city life.
By urbanization.
Exactly. We've noticed things with brown rats adjusting, like growing smaller rows of teeth, probably because they're feeding on human leftovers.
Oh, cool.
And not having to take on tough foods out in the wild. Fish that are now better at living in polluted water. This one was very interesting. It was a plant, the white clover. This was specifically noted in Toronto, that they produce less cyanide, which is typically their defense against herbivores, closer to the center of Toronto, where it is colder the closer you get, and plants that produce cyanide are more prone to freezing.
Oh.
So they are having to adapt to the climate change of the city and are now producing less of their toxins so that they can survive colder temperatures.
And probably fewer herbivores to worry about.
Yeah, I assume that there's not nearly as big a threat to being eaten when there's no deers allowed. And we see the opposite as well, because a lot of cities also show an increase in heat on average. That is a common feature.
The heat island effect.
Exactly. So we see lots of adjustments to higher heat tolerances. There was acorn ants have adapted to higher heat tolerances. And I think I saw one note that they are now thought to be better adapted to city life than the quote-unquote normal acorn ants are adapted to their wild environments.
Oh, wow.
That they have become that highly selected for. This is a huge area of study because, A, cities are the fastest growing ecosystem on the planet.
Yup.
Because we are making more of them all the time and expanding them.
Yep.
Yep.
Yeah.
And paving over other ecosystems to expand it.
Right. The cities are the ecosystem that devours other ecosystems.
Yeah. It's like a desert.
Ooh. A desert filled with humans.
Yes. And that was the other note, is that it contains more than half the human population. So it is a huge deal to understand, both from evolutionary standpoint, but also if we understand what's happening to the life in cities, we might be able to coexist or maintain it, or even control it better if we understand how the pests are evolving.
Mm-hmm.
Now, this review made the point that studying urban evolution won't necessarily reveal new insights into evolution, but it will allow us to ask questions in a new way, or to examine old questions. This could be a testing ground to kind of look at classic or long-standing questions about evolution in a way that we haven't previously. So we're probably not going to discover some new evolutionary trend, but we might be able to better understand some key aspects of evolution in this set environment that we can very easily reproduce the conditions of.
Yes.
Because we made it and we live next to it, so we have access to it.
Yeah. So a review paper like the one you're talking about is different, whereas most papers are doing original data, original research, some new information we haven't seen before. A review paper is collecting the information that has been gathered and the methods that have been used to basically give an overview. What have we learned? What have we done? And where do we go from here?
And that's where they're focusing on, is that we can ask some really good questions like, do different populations of the same species evolve in similar ways when faced with the same environment, but in different cities?
Mm-hmm.
Do different groups of life evolve the same features when faced with the same changes in their environment? So both of those questions can be answered here, but they make the point that it is difficult to study these because of how varied cities are, and that each city has its own features. They do have some similarities, like higher temperatures and pollution, but they also have different ages, different latitudes, different overall structure. So you can't compare each city one-to-one. One of the points they were trying to make in this review is that we need to have a standardized way to kind of evaluate how to compare and how to look at urban evolution across the board.
Yeah. How do we compare Toronto to Shanghai to Las Vegas?
Yes, exactly. The review aimed to develop a framework, which I wasn't able to find a detailed listing of because the paper is not yet accessible via other means.
Right.
But that's the goal, and that's what they were making the point that this is a really important area of study, but we need a framework to study it by. And they proposed a framework in this and are also proposing that this is an important area to continue focusing on and increase our focus on, because we might be able to improve cities with a better understanding of how it affects evolution.
That's a very cool field of research to discuss and to expand upon. Because so often when we talk about evolution and environmental change, we are looking into the past. But, especially these days, I feel like it's becoming more and more common and more relevant to study not only the evolution that is happening around us, but in particular, the way natural ecosystems and other species are responding to the ways we as humans are changing the environments. And so often that's hard to study.
Yes.
It can be very difficult to study. All right, we cut down this forest. Now what happened?
Yeah. What did that cause?
But this is an intriguingly, comparatively easy to study setting where, yeah, it's a city and there's tons of cities. We have a lot of case studies. We have a lot of examples. And we probably have decent historical records in some places to help us look back in time. So I can imagine this to be a very productive field of evolutionary study.
Yeah.
Very cool.
And the article for this is just chock-a-block full of awesome, interesting examples of evolutionary features we've noticed in urban life forms.
Those kinds of studies are also going to be very important for predicting what things will look like in the future. Mm-hmm. For example, in the next 10, 50, 100 years as our cities expand and as our ecosystems continue to change, but also like far, far into the future when Earth becomes Coruscant.
Yes, exactly.
Well, one more news for this episode now. You started off with crocs.
Yeah.
I don't have a news about snakes, but I do have a news that's going to let me talk a lot about snakes.
Very well.
This is research that presents one of the earliest records of a snake-like body plan, including limb loss, in land-dwelling animals.
That's pretty neat.
It's pretty cool. This is research by Arjan Mann, Jason Pardo, and Hilary Madden in the journal Nature, Ecology, and Evolution, and we will link in the blog post to an article in Live Science by Nicoletta Liness. As we've discussed before, particularly in episode 3 about snakes, what makes snake bodies unique and different from the typical land-dwelling animal body we think of is the combination of what is often called axial elongation, which means the body's really long, lots and lots of vertebrae, and reduced limbs or sometimes lost limbs. So the limbs are very small or sometimes missing. We associate this with snakes, but as we've discussed previously on the podcast, this has happened a lot. Most notably in squamates. Squamates are the group that includes lizards and snakes. Over 60 independent occurrences, that 60 different times this has happened, have been noted across living squamates.
Yeah. Yep.
And then if you go into the past, there's plenty more. There's a bunch more among amphibians, most notably caecilians, living amphibians, and a bunch of other extinct vertebrates. The extreme examples are snakes and also arguably caecilians, the amphibians, who are partially defined by having lost their limbs. Most snake-like lizards still have tiny limbs, although there are some others that have lost them. This paper finds a new example of a snake-like body plan in a new group, where we haven't seen quite this extent of snakiness before. They looked at 2 fossils from Mason Creek in Illinois. We discussed Mason Creek at length in episode 110. This is a roughly 308 million year old Carboniferous deposit that has tons of really well preserved, especially soft tissue fossils. The 2 fossils they identified of snake-like things are unique enough that they identified them as a new genus and species, Nagini masonense. Masonense is for the Mason Creek Formation, and Nagini comes from the Sanskrit for snake. The 2 specimens are one juvenile, a young specimen, and one adult. Based on the adult specimen, they're estimating that this species grew up to about 10 centimeters or 4 inches long.
Whoa.
Not very long at all. With 85 vertebrae, each with a rib pair. These are very well-preserved skeletons, including soft tissue remains, and they show a tiny hind limb pair and no evidence of front legs or even a pectoral girdle. The pectoral girdle is, your shoulder apparatus. They are completely missing that.
Wow.
This makes the body very snake-like. Long body, no front legs, tiny back legs. This is exciting for a whole bunch of reasons. Number one, these belong to a group of Carboniferous tetrapods known as Molgophids, which have been identified as an early branch of reptiles, possibly near the ancestry of reptiles. So these aren't squamates, they aren't archosaurs, they are way early reptiles. These also include a couple of other Mason Creek fossil species that are also somewhat snaky, long bodies and with small limbs. One of which, Jormungandr, we discussed in the news in episode 119.
Yeah.
You did that news.
I sure did.
I think you did that news.
If I didn't, it probably was still pretty good.
And the other one is called Infernovenator, which we should have done a news about.
Yeah, no.
That's awesome.
Jormungandr versus Infernovenator.
And now Nagini.
This Sunday.
Both of those other species have these long bodies with short legs, but Nagini is the first one of the group to demonstrate complete loss of one of its pairs of limbs. This is also exciting because if these are early reptiles, if these are in Amniota, the group that includes reptiles, birds, and mammals, this would be the earliest evidence of complete limb loss in amniotes. The first one that ever did it, before Sicilians, before snakes.
Pretty impressive.
It also shows a pattern of limb reduction and limb loss similar to what we see in snakes. Snakes also lost their front legs before their back legs over the course of their evolution.
Which is still just so alien to me. And I think it's probably just because of bipes.
And that's what I was going to say. There, we see the opposite in, for example, bipes, which is an amphisbaenid, which is what our Gorgon was in that spooky episode.
Yep.
But we also see the opposite in things like whales,
Yes.
which have reduced the hind limbs but kept the front limbs as their flippers.
Yep.
So we're seeing not only a snake-like body plan in these ancient early reptiles, but also snake-like evolutionary pattern. And indeed, some of those soft tissue impressions indicate that Nagini had a rounded snout, which the authors point out would have been good for face-first burrowing, which we see in a lot of lizards with reduced limbs and long bodies, and indeed has been proposed as possibly how snakes got started, as burrowing ancestors.
Which is immediately what came to mind for me, that if we're seeing similar body plan, similar body shape being evolved in both groups, and also evolving that shape in a similar series of steps, it seems, that seems like pretty strong. I mean, it's not guaranteed, but pretty strong evidence that you probably were evolving it for very similar reasons and very likely lifestyles.
And that ties into the other main point that I thought was really interesting about this paper, is they discuss the implications of this for how commonly we see this body shape and lifestyle show up, and for the places where we don't see it. The fact that we see this over and over and over again in lizards, in amphibians, in ancient tetrapods, and now in this very early, potentially amniote, suggests that the ability to do this evolutionary strategy is very ancient.
Yeah.
Possibly even more ancient because there are some even earlier tetrapods, some outside of amniotes, that show limb reduction, that this might just be a relatively easy thing for tetrapods, for land-dwelling vertebrates to do, in which case the groups where we haven't seen this happen, so notably mammals, we have never seen a snake mammal. We haven't seen it in archosaurs, that's your crocs and dinosaurs and birds. We haven't seen it in frogs. We haven't seen it in turtles. There are certain groups that notably haven't done this. And the authors point out it might be that those groups are unique.
Yeah.
That there is something about the developmental strategy in those groups or their evolutionary history that they have ended up with some sort of constraint.
Mm-hmm.
That means even if it would be beneficial, there are now too many obstacles in the way to evolving that, and they are no longer capable of doing it.
Yeah, because we've gotten long, skinny mammals, but they've never really gone snaky.
Right. And it might be, and I love when we get to point these kinds of things out, it might be that they're the weird ones.
Yes.
It's not that the snake things are weird. That's actually pretty common. The ones that aren't doing it are the odd ones out.
That's such a flip of everything, and it's so weird to think that it's like, what, all of you hang on to your legs?
Yeah.
Bizarre.
Why, you keep it, every one of you, even your burrowers?
All of your legs? All of them. That's fantastic.
Well, speaking of fossils...
Hey, we do that pretty often.
We do talk about that. Time to wrap up the news. Let's move into our main discussion. After this short musical interlude, we will get into our main topic of fossilization, which will retroactively add a layer of explanation to all that stuff we just talked about.
Yeah. Have you been waiting for our podcast to make sense? Now's the time.
Now, here it is. Stay tuned. Fossilization is the process of something becoming a fossil. It is the method by which we get fossils.
Yeah, it's a pretty straightforward term.
And thus, it is extremely important for us as paleontologists to understand as a process, because our main tool for understanding the ancient past is fossils, which means that fossilization is the filter through which we get basically all of our information on the history of the planet.
Without fossilization, doing paleontology becomes a lot more difficult.
Yeah. And so that means it is really important for us to understand what goes into this process and what goes into the different stages of fossilization, because, as I'm sure our listeners are already aware, it is not a perfect process. And the main theme of our whole discussion for this episode is going to be, how do we understand and deal with the fact that fossilization is not perfect? But before we can get into any of that stuff, we have to do a little bit of a definition here for the word fossil. We have gone 136 episodes of our paleontology podcast without really slowing down to define what this word means.
Everyone's been very confused. I'm sure they're going to explain it someday.
Eventually, we're going to catch up.
What was that again?
And one of the reasons why we haven't stopped to do this is because there isn't really a solid definition of what counts as a fossil.
Yeah, it's probably one of the most common questions that would come up while working at the museum or even just talking with kids about it. And it always seems like one of those, like, oh yeah, here, this is Shirley 101. Could you give us the definition of a fossil specifically, definitively?
Right.
Well...
And we've talked about this with lots of stuff, right? With the words like tree and words like...
Life.
Yes, absolutely. Fossil is a word, and I think part of the confusion is that fossil has been a word for so long that what it means has changed over time.
Yes.
These days, there are a couple of common definitions you'll sometimes see. So I have come across some people who argue that for something to be counted as a fossil, it needs to be at least partially mineralized. Mm-hmm. Turned to mineral or turned to stone, something like that. And I've seen some people insist upon that definition. That's a little bit of a strange definition if you start thinking about it, because that means that arguably things preserved in amber that aren't necessarily mineralized like we normally think of wouldn't be considered fossils, even though they can be 100 million years old.
Mm-hmm.
Other people use definitions that are based on age. So a common one that you'll often hear is 10,000 years. That if it is 10,000 years old or older, preserved remains, that counts as a fossil. That's another weird one because it's a very arbitrary line.
Yeah, what is magical about 10,000 years?
That one's a little bit odd to me because technically, if you're getting semantic about it, that would mean that something that wasn't a fossil a millennium ago is now a fossil?
Yep.
Because we have crossed the 10,000 year threshold. But I'll hear the 10,000 year one used a lot in schools. Like textbooks and then like younger kids' school lessons will use the 10,000 year line.
Mm-hmm.
One definition that I've heard that I actually came across while I was scouring the internet for what are there any that I haven't heard, was preserved remains of ancient living things from a past geologic age.
Oh.
Which is kind of a cool way to think about it.
Okay, yeah. Well, that I can see the logic there because the 10,000 years feels very, we threw a dart and went, all right, 10,000 years. That's where we're putting the distinction line. But a past geological age, we put those distinctions because a shift has happened.
Yes. And 10,000 years ago is roughly when the last geologic age, right, the Pleistocene, ended.
Yeah, so all right, that I could get behind that one a little bit.
Yeah. Suffice it to say, exactly where you draw the line between a 60 million year old dinosaur bone and a deer in the woods is kind of arbitrary one way or the other. The way when I get asked, when I have kids ask me, or even adults ask me in the museum, I say a fossil is the remains of a living thing from a long time ago.
Yeah, that's what I was going to say, is the remains of ancient life.
Yes.
That's how I describe them.
Sometimes you'll hear the term subfossil used for things that are old but not quite fitting whatever definition we're using for fossil. Typically, I'll see this used for things that are only a few thousand years old, things from the Holocene. So subfossil is another one of those. Sometimes it's used for stuff that's just not very fossilized.
It doesn't feel very fossil-y.
Or isn't very old. So you'll hear these terms kind of back and forth. Fortunately, for our purposes in today's episode, we don't actually need to have a solid line where we define fossil, which also happens to be the case for basically all of paleontology. It's why we've gotten this far without having an agreed upon definition across the board, because it's ancient stuff and that basically gets the job done.
Well, it's because, like, typically if you're dealing with an extinct species, unless you're dealing with a very recently extinct species, you're probably dealing with something that's so old that doesn't matter where the line is because you're nowhere near it.
Right. And even if you're younger, the kinds of studies you're doing are going to be very similar. And as we're going to discuss in this episode, however you define fossil, what counts is so variable that you have to account for differences anyway.
Yeah, and whether we use that term isn't going to actually change the information we're getting.
Exactly. Fossils come in a startling variety of shapes and sizes and types. Fossils can be the remains of anything once living. Animals, plants, fungi, algae, bacteria. They can be large. They can be tiny, microscopic. They can be traces left behind by living things like footprints and stuff. Fossils can be preserved in sediment. They can be preserved in amber or in ice or as just chemical traces. What we discuss as fossils is a very wide umbrella, and they can come in a huge variety of ages. As we've discussed on the podcast, the oldest definitely agreed upon fossils are at least 3.5 billion years old, and there are plenty of possible signs of life from even earlier than that. So our Earth is home to billions and billions, trillions per even, of fossils over billions of years, and that's only the ones we've found so far.
Yep.
The other thing that's always important to keep in mind about fossils, and thus the fossil record as a whole, is that they are basically always incomplete. Basically, every fossil is at least slightly different from what the original organic thing was. No dinosaur bone, no piece of wood from an ancient tree is the same as it was when it was alive, when it was initially buried. And lots of things don't get fossilized. So our fossil evidence is like I said, fossilization is a filter. We are always getting a altered version of our original material.
Yeah, it's always a fraction.
So, this brings me back to my original point. It is very important to understand the process of fossilization so that we are fully aware of what exactly it is we're getting. So with that, we can move on to what will be the bulk of this episode, which I have titled, How to Become a Fossil.
Oh, a handy-dandy guide.
This is going to be a step-by-step guide. You know, it's funny, There are a bunch of articles online that you can find that are how to become a fossil.
Yeah.
And it's talking about, what does fossilization take? And if you wanted to assure yourself to become a fossil, how should you go about it? We'll link to a couple of those in the blog post after the episode.
Amazing.
Now, there are many different ways that ancient remains can be preserved. You've got amber, you've got ice, you've got chemical traces. But the classic, and what we're going to focus on, the traditional, the most common version of fossil, is a thing that gets buried in sediment and preserved down there. So, how to become a fossil? Most of the time, step one is being buried under sediment.
Yep.
This goes for a tree, an animal, a bacterial mat, or whatever. Also goes for traces. Footprints, coprolites, anything like that.
And it's if you're doing a body, it's up to you whether you're alive or not when you're buried.
Every now and then I'll do presentations for school groups and kids about fossils and fossilization, and I like to bring up a kid to demonstrate how to become a fossil. And I'll bring them up and I'll say, all right, what kind of animal do you want to be? And they'll pick one. They'll be like, a bear. And I'm like, all right, cool. Act like a bear. And then they get into actor mode and they start acting like a bear. And then I say, all right, class, what has to happen to become a fossil? And they'll go, oh, you have to be buried. And I'll say, before that. And they'll go, oh, you have to, the bones have to come apart. And I go, before that. And then eventually they will go, the animal has to die. And then I will turn to the child and I will say, you have to be dead. And the great thing about elementary school kids is when they are already in acting like an animal mode and you tell them they have to be dead, basically without exception, in my experience, they will fall on the floor.
Yep.
Which is fantastic.
Yep.
But that is simplified. You don't technically have to be dead for the burial part to happen. There are plenty of examples of organisms being killed, of death and burial happening simultaneously.
Yeah, exactly. You can do those at the same time. Save a step,
That's
people.
Right. Cut out the middleman. The burial part of the process is key because underground is where most fossils are preserved. Being buried cuts off organic remains from all of the things that seek to destroy them up on the surface. If a body, and this is an animal body, this is a tree, whatever it is left up on the surface, it will inevitably, gradually fall apart.
Yeah.
Scavengers will eat the remains. Decomposers will break stuff down. Even if animals aren't eating it, they'll step on it and move stuff. Other animals or plants or fungi might start growing upon the remains. Water currents, wind, rain, light, oxygen, all of these are things that can move or break down or react with. Oxygen tends to react with a lot of the compounds in our bodies. So just being out in the open is exposing remains to all sorts of factors that are going to break them apart.
I mean, it makes me think of like when you were a kid and you left a toy out in the backyard versus when you put it away. And inevitably the one you leave in the backyard is now just a bit worse. It's a bit more brittle because of sun damage. It's bleached. Stuff might have started growing on it. It might have water damage. Like, it has been exposed to the elements, and those are destructive in and of themselves.
It's all the stuff that a museum collections room is designed to keep the specimens away from.
Yeah, are at war against.
But a little bit of burial just won't do. Because if you're too close to the surface, there's still activity. For proper preservation, organic remains need to be buried below the level where you've got burrowing organisms, roots of plants, freeze-thaw. If temperatures are shifting up on the surface, you need to be deeper than what I have seen called the biologically active zone.
Oh, nice.
I've also seen it called the taphonomically active zone.
Ooh,
and
cool.
I'm going to talk about that word here in just a second. Now, of course, all of these processes are complex. It is rarely as simple as thing dies, gets buried, becomes fossil. A thing can be buried in pieces. Something can be buried and then uncovered and then buried again. This process can be very complex, and that is part of what contributes to all the variation we see in fossils. Now, what we've been talking about so far falls under the topic of the study of taphonomy. Taphonomy, which we've mentioned on the podcast before, is the study of the fossilization process. It is the study of all the things that happen between when an organism dies and when we dig it up as a fossil. Taphonomy is, broadly speaking, this taphonomic process, the fossilization process, broadly speaking, can be split into two parts. The above ground parts and the below ground parts.
Makes sense.
All the stuff we've been talking about so far fall under what is called as biostratinomy. What happens before burial. And these processes tie into what is probably the most important concept in fossil studies of any kind, and it is a term we have used very often on the podcast, and that term is preservation bias.
Yep.
A bias, when we're talking about it in terms of science and in terms of study, means that our data is naturally skewed, that there is an inequality in what is getting to us. So many things can affect whether something becomes or does not become a fossil that what we get at the end of it is a biased sample. Not everything preserves and fossilizes equally. Not everything has an equal chance of making it to burial, becoming buried before any of these other elements manage to completely deteriorate the remains. Here are a few things that can get in the way of the burial process and thus have a huge impact on what actually makes it to the fossils.
A few things we hate.
Just a few things. One is just the anatomy of what is being preserved, right? Big things tend to survive longer than small things.
Mm-hmm.
Right? If you're subject to the elements, an entire tree is going to last a lot longer than a little mushroom, for example.
Yeah, we've talked about this with individual groups quite often as to the fact that your anatomy, how you're made and what you're made out of, is a huge factor into what groups preserve well and what groups preserve extremely poorly.
Yep. And that can include size and your composition.
Yes.
The classic example is hard versus soft parts.
Yep.
Bones and teeth and wood and exoskeleton, cuticle are much more resilient. They stand up to deterioration much better than soft stuff like skin and organ, tissues and organs and things like that, which tend to deteriorate very quickly. And so bones and teeth and wood are much more common as fossils because they just are more likely to end up buried and locked away from all these other factors. But it can go even further than just that. The actual chemical composition and structure can impact preservation potential. So, for example, we've talked on the podcast a bunch about a mineral, calcium carbonate, which typically we talk about in the form of calcite, which we see, for example, in the shells of brachiopods. It's very common in the shells of trilobites. There is an alternate version of calcium carbonate called aragonite, which is less stable, more prone to falling apart. Bivalves, so clams, oysters, mussels, things like that, build shells out of aragonite. Brachiopods, which are not quite clams, but they look a lot like clams, build their shells out of calcite, which means that brachiopods as an entire group are just more likely to preserve than bivalves are. Trilobites have more stable exoskeleton than most crustaceans like lobsters and shrimps and crabs and stuff, making them just more likely to be preserved. Even in our own bodies, and this is one we've talked about a whole bunch, go back to episode 88, teeth are much more resilient and durable and stable than our other bones. And bones are much more resilient and durable and stable than things like keratin in our fingernails or in animal horns and stuff like that. There's been research that has found that melanin, the pigment molecules that we find oftentimes in skin and hair, melanin helps make tissues more resistant to deterioration. So tissues with more melanin are less prone to fall apart. So like darker patches of skin or darker hair is, all else being equal, more likely to survive in the long term than lighter equivalents because of that chemical composition.
Yeah. Well, and it makes sense when you think of it from the anatomical side. Teeth are hard because of what they do.
Yeah.
You need your teeth to be hard, or else they're going to degrade very slowly as they crack and crumble while we chew anything that's softer than mushy stuff. So you need your teeth to be hard. You need your bones to be hard to hold you up. They're tough to survive the tasks in life, but it also makes them tough when it comes to surviving things after death.
Yes. And that skews our fossil records.
Mm-hmm.
Soft parts, soft-bodied things, less resilient things are simply less likely to make it to the preservational stage. Lifestyle can also affect whether or not you're likely to be fossils. For one thing, habitats. There are certain habitats that are just better.
Yep.
If you live in the water, if you're in a lake or a river or an ocean, those, shallow ocean especially, those are places where sediment is continuously being deposited. Whereas if you're high on a mountain, there's not a lot of new sediment being laid down up there, which means you're less likely to be buried.
Mm-hmm.
Environmental conditions can affect how much deterioration might happen out on the surface. Active water with lots of currents and waves is more likely to break down remains than calm water. Weather patterns, temperature, light levels, all of these things, which means that the season that it is might have an impact on fossilization potential, on burial potential. The latitude or altitude that you're at might have an impact, right? Things are going to have a different preservation potential in the tropics versus in the poles.
Yep. I always love the example of jungles, of rainforests and lush ecosystems, which are so full of life. It would make sense that we should get tons of fossils. If this has been tropical, this area, for a very long time, well, it should have been booming with life for millions of years.
Sure.
But one of the things about a rainforest is that it turns over its biomass aggressively.
Because it's booming with life.
Things get rotted and decomposed. There's not a thick soil layer because so much is growing and so much is using the nutrition that's available. So bodies do not last very long in a rainforest. So yeah, you actually get very little to no fossils.
Compared with something like a desert, where things are often likely to last in dry, arid environments, especially if you've got sandstorms coming through every now and then, even though deserts tend to have far less life than a thing like a rainforest.
Irony.
Organism behavior can affect preservation potential. Organisms that group together. If there's more of an organism, of a species in an area, statistically they are more likely that some of them will be preserved. Burrowers are more likely to be buried than animals that live up on the surface.
Self-barriers?
Yeah, they're doing the job themselves. We talked in episode 67 about the La Brea tar pits, and how the La Brea tar pits acted as a carnivore trap because food was available and carnivores would come in to get the food and get trapped at the site. We talked in episode 112 about caves and how predators using caves will bring their food into the cave, and that affects what's going to be buried and fossilized within the cave. So anatomy, lifestyle, behavior, your environment, all of these are things that can impact what is left behind as fossils, and this can make comparisons difficult. To use the example that you brought up, if we're comparing the fossil record of a rainforest and the fossil record of an ancient desert, we might look at two examples and go, oh yeah, well, we've got 10 species from this rainforest fossil site and 10 species from this ancient desert, but that does not mean that there was an equivalent population in these two ancient sites, even if we've sampled them just as extensively, because we have to keep in mind what the preservation bias is in those environments.
Yeah, it's important to know the background that you're dealing with. You can't just take the data at face value.
Yes. This can be difficult with comparing different fossil sites. It can be difficult with comparing different organisms. So if we're studying a fossil site and we've got 5 gator teeth and 5 leaves preserved in the sediment, that is not an indication that we had the same number of gators and trees in the site. Those two things preserve very differently. It can also make comparisons difficult over time because preservational biases have shifted over the history of the planet Earth. As climates have shifted, as continents have shifted. I was reading one book, I think this was in a book that I was looking through, that was pointing out that in the Paleozoic, much more landmass, continental landmass, was concentrated in the tropics, which meant there was lots of shallow tropical ocean environments, which are great for fossilization. These days, there's a lot more continental landmass in the northern hemisphere especially, in temperate zones, which means that the likelihood of getting wonderful tropical shallow ocean fossils preserved has been less for the last 300 million years than it was for the preceding 300 million years.
Well, and I think it's a really good point to make that it might be easy to think that the continents have moved around and throughout Earth's history, things have changed, but all the same habitats were still present. They were just shifting. But the truth is that there were periods where deserts were much more common because of the shape of the land and the positioning of the land. There were periods where coastlines were more abundant or less abundant. Like, we have had times in our Earth where this habitat was more rare just because of how things were lining up.
And we talked about this some in episode 115 about biomes, how they've changed over time. Also, organism anatomy has changed over time. We just mentioned that bones and teeth and shells and wood, for example, are better at preserving. They're more resilient, they're more likely to be preserved. But we also know that there was a time before bones and before teeth and before wood and before shells, or when those things were more or less abundant, which means that not only does this make it hard to compare different environments in the ancient past, it means that comparing a Cambrian fossil site with a Pleistocene fossil site is not going to be an equivalent comparison in terms of what is likely to preserve.
Well, and that concept right there was one of the big ideas as to why some people have suggested that there wasn't really a Cambrian explosion. It may have just been that fossilizable elements became much more common among organisms.
Right, that it skews what we're getting in the fossil record so that what originally looked like a very sudden appearance of things might have just been a change in the body structures.
Yeah. That instead of a bunch of life suddenly appearing, new traits suddenly appeared. And these new traits included hard parts that fossilized.
Right. Cambrian Explosion, episode 9.
Wow, that's so long ago.
Yeah. Also, Trees, episode 73, and Teeth, episode 88. We'll see if I can reference every other episode of the podcast. If any episode was going to do it, it would be this one. Trilobites, episode 82. We talked about that. Now, one of the books that I was looking through to review this topic pointed out, in a way that I think is really intuitive and a really good way to think about it. This book is Principles of Paleontology, which was one of my textbooks when I was an undergraduate, that people studying the fossil record tend to fall into two pitfalls of assumptions. The first assumption is that the fossil record can be taken at face value. That what we're getting in the fossil record is a direct representation of what used to be there, which is not true, as we've been discussing. The second pitfall is assuming that the fossil record is so incomplete that we can't get anything out of it.
Yes.
And I wanted to bring that up because we just spent a good chunk of time talking about all of the ways that the fossil record is unreliable. And you'd be forgiven if you turned off the podcast at this point and walked away going, man, paleontologists must just be making everything up.
Absolutely. Like, how in the world could you make any sense out of that nonsense?
And the answer is by understanding these processes.
Yeah.
Because that allows us to control for it, to adjust our expectations. One of the examples we just gave is, if we're comparing a rainforest and a desert fossil site, what we see is not directly comparable. But I don't think any professional paleontologist is going to think that it is. Because you've hopefully been trained to understand the nature of the fossil record. In the example where we have our lots of gator teeth and an equal number of leaves, that isn't an equivalent representation, but it is very informative because we know that gator teeth are much more likely to preserve than leaves, which tells us that we are getting something unusual at this site. that the leaves were either much more common or there was something about this site that made them more likely to preserve. I've seen this referred to as a taphonomic control.
Yeah.
So you can have at a fossil site certain types of fossils that should be very likely to preserve that can serve as your baseline. And most of the time, these are techniques that are being used in invertebrate sites, aquatic invertebrates. So if you have a fossil site and you're like, all right, we've got brachiopods and trilobites, we have a really good understanding. These are really good at fossilizing. This is sort of our baseline of fossilization potential. Everything else can be compared against this.
Yeah, we can account for the natural error, the natural bias that the fossil record introduces just by being so troublesome.
Mm-hmm.
And we can account for that by being aware that it is troublesome. Walking in knowing we're working against the odds of what was preserved, and so taking precautions, comparing to ecosystems as they are today, and comparing to well fossilized so that we can better understand the poor fossilized stuff.
And you'll often see this in paleontology studies, and we've talked about this in the news, where paleontologists will make those adjustments. Recently, one of the students at the university here presented her thesis presentation. So her thesis research, this was Sarah, and she was doing a comparison of the mammal fossil community at the Gray Fossil Site with modern mammal communities to estimate what kind of habitat it was.
Yes.
So here's a whole bunch of different features of mammals, what kind of teeth they have, what kind of diet they have, where they live within a habitat, and then throwing all that information into an algorithm to say, all right, here's what it often looks like, and here are the trends we see in these features in modern habitats. Here's what we see at the Gray Fossil Site. What does it match best?
Mm-hmm.
And I remember that she made the very important caveat. She said, before we get into all this, I just want to let everybody know, I completely removed bats from this analysis.
Mm-hmm. Mm-hmm.
Because bats are very abundant in mammal communities all over the world, but they are extremely rare as fossils. So Sarah explained that if you leave bats in the analysis, it completely throws off all your results.
Yeah.
Because your analysis is going to go, well, the Gray Fossil Site doesn't have any bats, which makes it a very weird habit. It must be something very bizarre.
It's Antarctica.
Right, exactly, right? The Gray Fossil Site does have bats, just not very many. But that's not the case. It's just that the fossil record isn't giving us that information.
Yeah,
so we make these adjustments.
Yeah, it's so far skewed that taking it in the group of all the rest of the data will actually throw off the analysis. It's like if you were studying historical groups of people and you had a whole bunch from one age and then you just decided to include one civilization that was thousands of years older just to see. Well, it's going to throw everything off because those ages can't be compared. You know, the Stone Age versus the Bronze Age.
Right.
You can't say those are the same situation.
Right. If you want to take the average weight of mammals in this apartment,
yes,
your average weight is going to be very small.
Oh yeah,
like shockingly small because there's a cat skewing the data.
You're gonna assume a bunch of kids in a trench coat,
yes,
rented this apartment on a lease,
started a podcast. Importantly, understanding these different types of preservation bias not only lets us sort through the data, but it also lets us predict fossilization patterns. We can predict what kinds of fossils, what kinds of organisms, what kinds of body parts are more likely to preserve, and build studies and analyses based off of that. This is why so many studies focus on teeth. They'll say, all right, we're going to go to this site and sample all the teeth, because you can be pretty sure you're going to get teeth.
Yes.
As opposed to, all right, let's go to a site and try to sample all the fossilized hair, because that's just not a realistic expectation.
Because it's going to be a lot of, hey, can we sample your hair? None? Okay, on to the next place.
Yep. And it also allows us to understand what's missing.
Mm-hmm.
Soft parts typically don't preserve. Internal structures typically don't preserve. These are things that, as long as we are understanding that we are missing them and why we're missing them, we can adjust our understanding accordingly.
The taphonomic side of paleontology by far feels like one of the most Sherlock Holmes detective novels side and aspect of this science, because so much of it is not just taking into account what clues are there, but what clues aren't there, and why the clues that you have are the ones you have, and forming as complete a picture as you can from all of those both missing and present bits.
Yes. Well, and it is, I often relate paleontology to forensic investigation.
Absolutely.
That, yeah, you're working from incomplete information, but as long as you understand what's missing and what the processes are, you can account for that. Now, so far in our discussion, we have only dealt with that first part of the fossilization process, the getting to burial part.
Yeah, staying together long enough to get underground.
Yes. But I'm sure many of the people listening to this episode are waiting for us to get to the next part, which is often called diagenesis. And that is the transformation. Once organic remains have been buried and they're locked away and they're protected from all of the changes in the elements, changes begin to occur. Right? A fossil, like we said, is not exactly what it used to be. There are many different modes of fossilization, things that can happen to alter and preserve the remains after they've been buried and before we finally get a hold of them. So after the break, we are going to dig deep, I guess, and explore how do organic remains transform into what we're commonly familiar with as fossils. Stay tuned. To go back to my example from earlier, when I talk to kids in classrooms about fossilization, they often are very familiar with the first part, the burial part.
Yes.
The remains have to be buried, but what they often need to be reminded, or sometimes taught, is that that's not the only thing, right? And the way that I often put it is, yes, here is Susie, who was a bear and is now dead on the floor. If we just kick some sand over him, that's not a fossil.
No.
Fossilization oftentimes is a process of chemical and physical changes to the material that is being preserved.
Yeah, when we dig up dinosaur bones, they're not just bones that were underground. They're altered.
And very briefly, before we talk about the changes that happen to the fossilizing things, I want to talk a bit about sediment. Fossils are buried typically, not always, typically in sediment. Sand, silt, clay, ash, some kind of loose, unconsolidated stuff that can bury the fossil. We talked in episode 131 about how lava does not do a very good job burying fossils. Usually it has to be grainy stuff.
Yep.
Sediment is where we get most of our famous rocks from. Sandstone used to be sand, and mudstone used to be mud, and siltstone used to be silt. Diagenesis, this preservation, this lithification process, is something that happens to fossils. It also happens to sediment. The transformation, for example, of sand into sandstone is a combination of compaction, which is that under pressure, when it is buried deep underground, the pressure of all the earth above it is squeezing the sediment together. So all the grains, all the little sand grains, the space between the grains is being reduced. It is shrinking, expelling fluids that might be trapped in there or gases that might be trapped in there. The grains are actually getting crushed together so that they are growing closer and closer. And at the same time, typically they are subjected to groundwater.
Yep.
This is an important component of this stage of long-term preservation. Water moving through this sediment will do the dual jobs of dissolving stuff and depositing stuff. We talked about this in the caves episode 112. Water will dissolve calcium carbonate off the walls of the cave and then drop it off somewhere else. As water flows through compacted sediment, it will be dissolving some minerals and then precipitating them, like depositing them, laying them down in the remaining pore spaces.
Yep.
So as sand or silt or ash or whatever it is being lithified, it's because it is being compacted, and the spaces are not only shrinking but being filled in, which is a process that tends to happen better under higher temperatures as well. Heat and pressure tend to be part of this lithification process. And if there are organic remains buried within that sediment, a similar thing will happen to them. So let's get to some of the meat of the episode, and that is how physically, chemically, does something transform into a fossil. The most common style of fossilization, the most intuitive, when we think of a fossil, what we're typically thinking of are remains that have undergone a combination of permineralization and replacement. Some combination of those two. Permineralization is the process by which minerals fill in the spaces.
Yep.
So you have a bone, the organic stuff has typically decayed away because it usually does, so you've got empty space inside the bone. Minerals will fill in that empty space, seeping in, hardening, and forming a preservational structure that actually helps the fossil keep its structure and stay preserved. Oftentimes the mineral that's going in there can be silica, which is our most common mineral up here on the surface of the Earth, silicon dioxide, phosphate, other things like that. A lot of dinosaur bones are permineralized. Petrified wood is often permineralized wood.
Yeah, this is the petrification is referring to.
Yes, like literally being filled in with mineral to create a solid chunk of a combination usually of original material, original bone mineral or tooth mineral or wood structure, with additional minerals filling in all the spaces. The most intuitive version of this, I think, is like, yeah, the holes inside bones, the pores in wood. But in some cases, this mineral deposition can happen at such fine scales. It can be the space between cell walls. Mm-hmm. It can preserve really fine details. This is how you can get things like growth bands and shell layers and even cell structures. If the mineralization process is happening at this fine enough scale, as groundwater flows across the fossil, dissolving some stuff as it goes and depositing these minerals in all those spaces. This is part of how we can get those really detailed microscopic analyses of fossils.
I remember when I was a kid and I first learned about permineralized bones and that it's filling it in with minerals, I was thinking of it from like the hollow sections in the middle where the marrow used to be.
Right, like sand filling in an empty space.
Exactly. And I was like, well, how in the world does that preserve the whole bone? Wouldn't the bone still deteriorate and then we'd have these chunks of marrow-shaped minerals?
Right.
Which is still cool. That's awesome, but that you can't make a skeleton out of that. So I couldn't understand it. But that's because you can't think of it from our eyeball scale. You have to think of like an electron microscope sees stuff. When you zoom in on bone, it's porous and fibrous, and it is incredibly full of spaces that just to us look smooth.
And the minerals being deposited don't have to be big grains of sand. They can be tiny, tiny crystals.
Yes.
The other common process that often happens in conjunction with this, not always, is replacement. And in replacement, instead of filling in the empty spaces, minerals are replacing the original material. So water over time is dissolving, reacting with bone or wood or whatever the original material is, and depositing new minerals in the place.
Yeah.
Now, sometimes if this happens relatively quickly, it can be a very messy process. It can leave a chunk of mineral that vaguely resembles what it originally was. But if it is slow and gradual enough, this can be replacement on extremely fine scales. I've seen it in one source described it as sometimes molecule by molecule. Just dissolving out a little bit of bone and depositing a little bit of silica.
That's amazing.
And the way to think about it, the way that I've been thinking about it is like if you had a giant house and you went through and one by one replaced all the bricks with bricks of a different color.
Yeah.
Eventually, what happens is your entire structure is fully replaced. This is the ship of Theseus.
Exactly, yeah.
The whole thing is now a different thing than it originally was.
And like you were saying, if it happens quickly, it makes sense that it's going to be messy because the rate of dissolving and the rate of depositing are not, it's not a system that is being regulated. They're happening at their own pace. So if it happens quickly, you could dissolve way too quickly or deposit way too quickly, and you could build up too much or dissolve a chunk that does not get replaced.
Mm-hmm.
But if it's happening slowly, even if those rates aren't perfect, if you're going very slowly, the amount you can mess up is much smaller.
Yes.
So you get nice and you get some crazy awesome fossils with this technique.
Yes. So both of these techniques, replacement and permineralization, can end up filling or replacing fossilized material with silica, so you get something that is basically turned into quartz.
Mm-hmm.
Pyrite, so you can get pyritized fossils. This is my favorite.
Yes,
where
same.
If what is being deposited is iron and sulfur, iron sulfide, it's fool's gold.
Yes.
So you can get these ammonites or brachiopod shells that have basically been turned in. This is some alchemy stuff.
This is Midas touch.
Yeah, turned into gold. Not real, it's fool's gold. But you get these cool pyritized fossils. This is also how you can get opalized fossils. Opal is a version of silica, so you can get this opalization. This is a big part of the reason why fossils tend to take on attributes of the surrounding sediment. At the gray fossil site, our fossils are this dark brown color, because that's the kind of sediment that's surrounding them.
Yeah,
it's essentially a stain that can never go away.
Exactly. It has permanently been colored by the minerals and materials in that clay.
This is also why you can get radioactive dinosaur bones in some places.
Yeah.
Because if they're buried in mildly radioactive sediments, the fossils themselves will eventually become radioactive as they are mineralized and replaced with the surrounding minerals.
If you eat one of those, that's how you become Dino Man.
That's right. Don't try this at home. This podcast is not medical advice. You can also get a process called recrystallization, where the heat and pressure that a fossil is underneath converts the minerals to a different form of mineral.
Yeah.
So you can get silica to quartz, you can get aragonite to calcite. All of these are the processes by which a fossil quite literally becomes petrified, becomes mineral, more mineral, and stone. But the important part of all of this, of understanding all of this process, isn't just to know this cool factoid about, yes, this is how a fossil becomes a fossil, but to understand what this means for us who are trying to study it. What kind of thing are we left with when this process is done? These processes can all preserve exceptional detail under the right circumstances. Usually, they are preserving hard stuff. Now, these are processes that are going to happen over a long period of time. So oftentimes, soft things are already deteriorated. They're already decayed. There are cases where soft tissue can be mineralized if it is buried quickly enough, if it is preserved quickly enough, removed from places of decomposition and such. But this process also tends to be missing at least some information. Often the information is the stuff that has disappeared. Soft tissue, molecular things, right? DNA does not typically preserve very well in this kind of fossilization because it is long gone. If things are being replaced, so if your original tissues are being replaced by surrounding minerals, that can alter the shape of certain things. Recrystallization can alter the shape of certain things. This process tends to change the color and texture and density of the fossils themselves. And fossils that are formed this way are very commonly deformed.
Yep.
Because the heat and pressure that is creating the fossilization situation, the conditions needed for this, also can warp and crush and cause the fossil itself to become misshapen.
Yeah, we tend to think of things like bone and teeth and so forth as incredibly rigid structures. And so if you were to put pressure on it, it's just going to snap or crush or break.
Right.
But when you put a lot of pressure on something
over a long period of time
with heat, and when it is compacted on all sides so it does not have room to shatter, it can get smushed. It can get like Play-Doh. It can get mushed a little bit. Not a lot, it's not going to be turned into a puddle, but you can have actual deformation, not cracks, but it has been warped.
So this is a process that can give us some excellent fossils, but with caveats that are important to understand. Other forms of fossilization that happen deep underground include things like molds and casts. So a mold is when sediment surrounds a fossil and then the original material, a shell or whatever, completely disappears. It gets dissolved away, it falls apart, whatever happens. What you're left with is a hole in the shape of the original thing. If that hole gets filled in with new sediment, like if it gets filled in with silica, you now have a chunk of silica that is the shape of the original shell or bone or whatever it was.
It's kind of a version of the replacement, where
But you're replacing the whole thing.
you're replacing the cavity that it filled.
These are really handy and really common in the fossil record, but of course they only produce part of the structure. You're only getting the outer shape of the structure, or sometimes the inner shape. So molds and casts especially, can give us really cool insights into things like brain cases.
Yeah.
We talked about this in episode 121 about brains. That, yeah, if a brain case of a skull gets filled in with sediment and then the skull goes away, you have the preserved shape inside the bone, which it can often be hard for us to study in other fossilization situations. Another famous form of fossilization is carbonization. This is something that usually happens to softer things, so leaves, worms, a lot of Cambrian stuff, like at the Burgess Shale is fossilized this way, where something is flattened between sediment layers, and it is squished down into a cartoonish, paper-thin
Flat world
version of itself, and once again, heat and pressure tends to cause reactions that release certain elements like hydrogen and oxygen. Basically, it squeezes out most of the stuff that can be squeezed out, and what you're left with is a carbon film, a dark film that looks like a stain on the sediment that can give you the shape of a worm or a leaf or something. These, once again, have these caveats that they are highly changed.
Yeah.
That they are, the shape of them, they are squished, the chemistry is very intensely changed from what it once was. But you can also get evidence of soft structures like eyes and internal organs in this way.
Yeah, it makes me think of an X-ray, because quite frankly, a lot of them look like X-rays.
Yeah.
Where you're getting glimpses of the internal structure because that also got compressed. But much like an X-ray, it can be very difficult to read and misleading if you don't know how to interpret things.
Yes.
Because you're seeing all the layers of the body crushed into one.
Yes.
and that's not how your body usually is. So it skews what you're actually seeing.
Now, of course, with all these different forms of fossilization, there is a spectrum. There is a gradient from not great fossilization to excellent fossilization.
Yeah.
So this is a great time for us to introduce another term, another vocabulary word that I'm sure many of our listeners have heard, and that is Lagerstätten. A Lagerstätte, or plural Lagerstätten, are sites of exceptional preservation. This is a term you'll hear a lot in paleontology, which, once again, this is a term that I don't think there's like a hard line as to what counts.
Yes.
It's just a site where it's great. And we're really happy about it.
It's basically, you kind of know you have a Lagerstätte because when you look at it, you go, wow.
Yes. And Lagerstätten can either preserve a lot of stuff, so like a bone bed might be considered Lagerstätte, or very well-preserved remains, or both. The Burgess Shale, episode 89, is considered Lagerstätte. The Solenhofen limestone, where Archaeopteryx comes from, I have heard some scientists refer to the Gray Fossil Site, episode 14, as a Lagerstätte deposit because of just the high level of fossil preservation we get.
Yeah.
Lagerstätte often are famous for producing full remains, full skeletons, full trees or whatever, soft body parts, lots of plants, especially soft things. There are some that provide things like embryos. Embryo like inside of eggs, but also like just microscopic embryos of things like certain Chinese fossil sites. Microscopic details of fossils, a lot of feather preservation also in a lot of Chinese fossil sites. These are places where all of the circumstances have come together, that how things are being buried, what's being buried, the conditions of fossilization and preservation have lined up just right to give us some really exquisite preservation.
Yeah, because as we were saying in part one, so much of what can happen to fossils is working against us, or we're having to work with what it leaves us, all the things that can destroy it and ruin and change a fossil. But by that logic, statistically, there are going to be situations where everything goes the way we'd like it to.
Yeah. Now, it's important to remember, even at the best fossil sites, we are still getting a skewed picture. For whatever the preservation situation is, we always have to keep in mind, right? The Burgess Shale produces a lot of those flattened, carbonized fossils. The Maison Creek, episode 110, gives us stuff like that, which are great, but always keeping those caveats in mind of what we're missing with our various fossils.
Yeah. Still not everyone who dies is getting fossilized, and we still don't get the animal or the plant.
Mm-hmm.
It is still what is left.
Now, this has been mostly talking about the classic buried and turned to rock kind of fossils. There are, of course, other kinds of preservation in the long term. I am going to go through these quickly, just as a couple of notes, because I want to mention them, but most of these, for one reason or another, we're not going to discuss them in detail here. For example, fossils often come preserved in amber.
Yep.
Amber is resin that comes off of trees. We did a whole episode about this, episode 62. Go check it out. Amber often preserves full bodies, body tissues and bones and everything, but tends to be limited to small things and certain places and times. Caves are good for preservation because oftentimes they are dry and stable environments, or they're wet and stable environments where things can be covered over in sediment or in mineralization without being disturbed very much. These are very good for recent fossils. We did a whole episode about them, episode 112. You can get trace fossils. We did a whole episode about them, episode 118. This is great. Every episode should be like this. You can get fossil remains preserved in ice, where we've gotten things like cave lions and mammoths, which is great preservation of tissues, even proteins and DNA, but limited to recent stuff, because ice just doesn't last that long on the planet Earth.
Yep.
You can get things like bog bodies, which are pickled, right, preserved in peat bogs, which is great for preserving tissues, but bad for preserving bones and genetic material most of the time. So there's all these different circumstances, and they all have their caveats and things you need to understand about the mode of preservation. And then, of course, there is the almost separate discussion. It is its own category of discussion, and maybe an episode in the future, of chemical and molecular fossils, where you are getting remains that are not an organism or a body part, but chemical breakdown products. Sometimes these are the microscopic chemical remnants of things that used to be in the body, of pigment molecules or something. Sometimes these are traces in the sediment that are the byproduct of life processes, which is a type of trace fossil. And then, of course, there is biomolecules like DNA and ancient proteins. We did a whole episode about ancient DNA, episode 34, but to mention it briefly here, we can get ancient DNA and proteins, especially from cave and ice and permafrost remains that are relatively recent. In the last several years, there have been multiple reports of hints of ancient proteins and ancient DNA going back as far as the Mesozoic, in dinosaurs and plants, at least as far as the Jurassic, from what I remember reading. And there has been lots of discussion about what kind of preservation might lead to the long-term stability of these kinds of molecules. Because for a very long time, we thought that that can't happen.
Yeah, that was just one of those cut and dry. You will not get molecular material. You will not get proteins. You'll not get the stuff inside the cells.
Right.
Sorry, it's just not going to happen.
And so there's been lots of discussion, on the one hand, about if this is actually happening. There's a lot of skepticism among certain scientists as to how many of these reports are really reliable, or are we misidentifying things?
Yeah, very often when a new study comes out, there will be researchers who bring it into question, or give alternate explanations to what could answer this finding.
And we've talked about that in the news a bunch in previous episodes. And then there's been a lot of discussion of if that is what we're getting, why and how. Because understanding how can also give us clues as to where to look for more.
Yeah, we might have been missing it if we were looking at fossil sites that would preserve this, but we didn't know to keep an eye out for it.
So there have been some suggestions. Certain types of bones might be better, so denser bones. So for recent studies, the petrosal bone, which is part of your ear apparatus, is one of the best bones for getting DNA, because it's a dense bone that preserves internal stuff well. There's been a lot of talk about what's called cross-linking, which is when a protein or even a genetic molecule gains more bonds within itself, sort of gets all tangled in on itself, which, if it happens in a living thing, is terrible and toxic, and it makes everything go haywire, but might be a process that is helping stabilize these molecules in the long term. There's been a lot of discussion trying to get at the kind of understanding we were just talking about for permineralization and replacement and all that, because if we can understand how this is happening, that allows us to do all the other stuff. That allows us to correct for what we're seeing and not seeing. It allows us to predict where we might look to find more examples of this. This is a really cool topic because it is an area where we are currently investigating and learning how does this kind of fossilization happen.
Every bit of research on this topic and looking into this concept, you are witnessing the cutting edge of this category of fossilization.
Yes. And this brings us to our last major question, our last major topic for our discussion in this episode, and that is, how do we study the process of fossilization? Now, I mentioned earlier that the study of fossilization is taphonomy. There's a whole lot to say about taphonomy. This is not a taphonomy episode, despite being a fossilization episode. That we can do a whole separate episode on taphonomy if you want to hear more about it.
Absolutely.
But in brief, there are a number of different ways we can go about examining the process. One is just examining the fossils we find.
Mm-hmm.
What condition are they in? How has their chemistry been altered? That helps us to understand what is happening to them during the taphonomic process, during the fossilization process. Another very common method of studying the fossilization process is field tests, field observations, and field experiments, which basically means watching stuff decay and get buried and fall apart in nature.
Yes.
In our modern world. There are tons of studies that will watch death and decay and the disintegration and burial of remains of animals and plants. I had a colleague when I was an undergrad, Lauren, who was doing studies on taphonomy using deer carcasses, and she would have a deer carcass in a strategic location around campus, like the outskirts of campus, and then visit it every now and then and record what were scavengers doing, how was the body changing, how quickly was it being covered up or broken down, to help us understand what happens to a body, to an organism in different conditions, in different habitats, etc. We do the same thing with forensic studies.
Yep.
Not too far from here is a place called the Body Farm.
Yep, I was going to bring it up.
Yep.
It's fascinating. It's awesome.
Where they do the same thing, but with human remains, for the purposes of for forensic science.
Mm-hmm.
To know, okay, yes, if a body is left in a river, or if a body is, surrounded by plastic or something, how does that affect the deterioration process?
Yeah, well, and this is how we can, when you see cop shows where they'll come and they'll go, well, according to the body, they've been dead for. This kind of research is how we get that information, is by putting bodies in different situations and then checking on them at day 1, day 2, day 3, day 4, and that gives us information. Go, roughly, this looks the same as they look after 4 days.
Yep.
And we've talked about this in the news, the gator study, where they bolted the gators down at the depths to see what scavengers would go after
down
a large marine.
in the ocean.
Mm-hmm.
Yep.
To see what scavengers would handle large marine reptiles, so that we could get an idea of what might have been scavenging mosasaurs and plesiosaurs and ichthyosaurs.
Yes. And in addition to field studies, we can also do lab experiments on fossilization processes. One example, I'm just going to give a couple of examples, but one common example to study deterioration of fossils is to use basically water flumes to do transport experiments.
Yep.
So one example that I came across of this was a 1990s study that did this with urchins. And they call these tumbler experiments, where they tumble it in flowing water to see how it breaks down over time. And what's really cool with experiments like this is you can determine how the surrounding conditions affect the process. So the 1990 study found that urchins being tumbled in moving water break down more readily, more quickly in higher temperature water.
That makes sense.
That the temperature impacts the deterioration process.
It's like mixing your sugar into tea and whatnot.
Sure.
If it's warm, you're going to dissolve the sugar much quicker.
Yes.
That's cool.
And then there are also other experiments that are basically lab-grown fossils.
Yep.
So these are often called maturation experiments. So what a lab will do is they will get organic remains and put them in some kind of container or some kind of sediment and subject them to intense heat and pressure to try to accelerate the kinds of chemical and physical reactions that lead to fossilization.
I find these fascinating.
So they're basically making fast fossils. There was one study that came out. I think we talked about this. This was a 2018 study. I think we did this in the news. I think this was the one where they were calling them easy bake fossils.
Oh, yeah.
And this was a study where what they were doing differently was using sediment, porous sediment to surround the remains, and then subjecting that to heat and pressure to try to get more realistic results. But basically what these kinds of experiments are trying to do is speed up the natural process and give us something that approximates a natural fossil so we can study the process under different conditions and with different variables. This has become really useful, a really big deal in recent studies of molecular preservation.
Yes.
These in that 2018 study are often looking at what is the chemical remnants? What are we seeing happening to proteins and to different body structures when we do our accelerated fossilization process?
Yeah, our simulated fossilization.
And we should point out that as with everything, there are caveats, there are pluses and minuses. These do not create an exact same thing as a natural fossil.
And I know at least back in those days, lots of researchers who were unsure of the reliability of these techniques. Mm-hmm. So like not everyone's in agreement that these are for sure ways to give us glimpses into what these materials would look like. But the nice thing is if it is giving us a somewhat accurate view of how these things will degrade and change with the heat and the pressure, is that we know what they look like beforehand.
Yes.
And in a lab situation, we can make sure there's no outside contaminants that could be skewing things in a weird way. Because that's a big question is, are we seeing proteins or are we seeing proteins from the animal or proteins from something else that grew on that after the fact? Right. Whose proteins are these? And trying to determine that with these experiments can give us that before and after image that we don't get.
Yes. And that 2018 study was in part introducing a new technique that they were proposing, at least, was more accurate as a simulation of real world, so natural fossilization. So it is a type of experiment that is still being worked on and refined, which is pretty cool.
Well, and that's the cool thing is that in those early ones, when researchers came out and said, I don't actually know that this works the way you're saying it works. Mm-hmm. That doesn't mean, all right, throw it out, move on. No, that's a valid reason to go, okay, well, how can we make it work the way we're hoping for it to work? Like what steps can we take to make it more realistic?
Yes.
And that's what's happening. So I would love for 20 years from now us to have these labs where it's just these fossil ovens that you can put things in and get a simulation of what some of its materials would look like after aeons of fossilization.
And all of this ties back to our central theme of today's discussion, which is how we understand fossils, how we understand the fossilization process, and how we understand the filter that the things we're studying went through before they got to us. As I said at the beginning, understanding what's happening to these things is crucial for us to interpret them accurately. And in this episode, we've discussed what fossils are and how they form and how fossils are how the fossilization process is biased towards certain habitats and certain organisms, why this information is important, and how we are continually studying and learning and refining our understanding of these processes. If you'd like to hear more discussion about more specific types of preservation or studies in fossils, please refer to the previous 136 episodes of this podcast. This might be the most broadly applicable episode topic to our own podcast that we've ever done. You should really listen to this one first.
Yeah, there you go.
This really should have been episode 1.
Well, I love the concept of studying fossilization because we always talk about studying fossils and what that can tell us about the living organisms that they once were, or the environment that they once occupied, or what that tells us about how the landscape of the planet has shifted. But we don't often talk about what the process that gave us that fossil tells us and how that informs us. It makes me think of a conversation I was having with my girlfriend about historical observation. And when studying historical documents, you have to take in consideration that basically every bit of data we have from human history is biased because it was written down by someone.
Yeah, someone made that.
Someone who could have been lying, who could have had a grudge, who could have been jealous, who could be a winner, who could be a loser.
Mm-hmm.
We are biased animals. Our opinions run through everything we do. So when we write down documents, it is inherently a little misleading because you're taking it from that person's perspective.
Yes, and you have to know that.
You have to take it from a historian's view, accounting for that bias. We have to do the same thing with fossils, but we can also learn a ton based on what we do have and how it got here. Mm-hmm. How it got preserved can tell us a ton, even though we're still missing a bunch because not all of it got fossilized.
As usual, this is, of course, an enormous topic. There are many branches off of this subject that we could devote further discussion to if our audience would like to hear it. So if there's anything that we've touched on in this episode that you'd like to hear us talk about more, please feel free to send it to us as a request. But before we wrap up our discussion, there is one last thing for us to do, and that is our patron question. One of the gifts that our supporters can get on Patreon is the ability to submit questions for us to answer here on the podcast. Now, we actually did have a patron question from Jackie who asked how fossilization can preserve such fine details, which I think we have sufficiently answered earlier in this episode. So thank you for that question.
Longest patron question answer in history.
This was an hour-long answer to your question. So we are going to answer another patron question here at the end of the episode. Will, what is our patron question of the episode?
Our question is from Suzanne, who asks, in a previous episode, you guys mentioned that we only have a single specimen of Carnotaurus. How can scientists be sure that this individual was a distinct species and not just a badly deformed member of an already known species?
That is a great question.
Excellent question.
And applicable to today's discussion.
Yep.
Carnotaurus, of course, is a theropod dinosaur from South America. It's the meat-eating dinosaur with the short pit bull face and the horns over its eyes.
Yep. From Disney's Dinosaur, it's the bad guys.
There you go. This is a great question. If we only have one specimen, how do we know that it's not just a weird, deformed, messed up specimen? And the answer, in short, is that deformation of either a fossil or a living organism tends to leave clues in the specimen itself.
Yes.
So if a fossil gets deformed in the process or its shape gets changed, often we can find evidence of that in the physical structure of it or clues towards that in understanding how it was fossilized, going back to our earlier discussion. And as we talked about in episode 84 about paleopathology, if a fossil injuries and disease and deformations tend to leave signatures in the bones or even wood or seeds or whatever organism it is, so you can look for these clues that something's not quite right. It won't look quite right.
It makes me think of the answer that we'll often give when people ask, well, how do you tell the difference between a rock and a bone? And, internal structurally and chemically, there's lots of ways, but typically they mean when you're digging.
Right.
When you're digging, how do you know that you didn't just dig up a rock versus a bone? And the answer is, well, a bone looks like a bone. It has bone-like structure. Rocks don't form in bone-like shapes because a rock doesn't need to support the weight of an animal. It doesn't need to have a hinge-like movement or muscle attachment. So bones have all those shapes for specific reasons. But a diseased or a deformed bone is often altered in a non-uniform, a unnatural way. It's messed up because that's not how the bone's supposed to be growing or supposed to be developing. So you can find abnormalities, things that stand out from the typical anatomy of the bone.
Yes. Now, having only a single specimen does make it hard to answer certain questions, like, for example, what is the average size of this ancient species?
Yeah.
Right. Is our one specimen a giant? Like, is this the biggest one that ever lived? Is it a small one? Are its proportions typical for this species? Does this one have oddly short legs?
Yeah.
A species can have a lot of variation within, even without being deformed or dramatically different.
Well, especially we have one that has two really ridiculous horn structures on its face.
Mm-hmm.
Unusual among predatory dinosaurs. Was that because this was a male?
Right.
And that was display structures? Did both male and females have these equally? Did one have smaller horns versus the other?
Did this change as they got older?
Yeah. Was there diversity among the horns of subspecies of carnivores?
Right.
We don't know all of that because, we only have this one horned individual.
So we have enough with Carnotaurus, and it is well preserved enough that scientists are pretty confident in saying, these features are natural features, normal features that differentiate this from any other known species. But we don't have enough to know how much of what we're seeing is typical for that species.
Yeah.
And that'll just come with more fossil discoveries. Excellent question, Suzanne. Thank you so much for that. Thank you to all of our patrons. Thank you to everyone who requested this episode topic. I've had a lot of fun discussing this very foundational, fundamental conversation to have.
Yeah, well, this is a fun one because we so often talk about, we mention preservation bias quite often. And we talk about after the fact when we have the fossil. Talking about that process gets skipped over so often, but it really is crucial and critical.
Yes. So consider this required listening. Now that you've gotten to the end of the episode and that caveat does not mean anything, congratulations. You did it. You made it. Like I said, if you have topics in mind you'd like to hear us discuss, please feel free to reach out to us and let us know. You can follow us on the social media, send us email, send us physical mail, however you want to get in touch with us. Every episode there is a blog post afterwards on our WordPress blog, where you can find photos and links for more information. You can find a link to the blog in the episode description, along with various ways to support us, links to our Patreon, links to our social media, links to our new Discord server that we set up recently that people have been having a lot of fun on.
Yeah.
Thanks as always for listening. We release episodes every fortnight, so join us next time where we will talk about something else that people have asked us to talk about.
that we also should have done at the very beginning, maybe.
Oh, yeah, maybe. We'll start going back. We're going to start the Common Descent podcast right here. Episode 1 coming up next.
What is a scientist?
Bye, everybody. Thanks for listening to the Common Descent podcast. You can follow us on Facebook, Twitter, YouTube, and check our WordPress blog for pictures and links after each episode. Huge thanks to our patrons whose support helps keep this podcast running and who get access to bonus goodies on Patreon. The song you're hearing is called On the Origin of Species by Protodome, which we found at ocremix.org. Thanks again for listening. We hope you'll join us next time.